In a previous video, I used a neural net regression code to demonstrate overfitting here. So as you see here, if you run a lot of epochs, the error for the training set gets very, very small. So you can see all both the blue and the orange line go through the points, right? But for the validation set, which are not used for the training, the error is larger. So that's a sure sign of overfitting. In this video, I want to talk about another way of avoiding this, another regularization method called dropout. So dropout is based on kind of a crazy idea that actually works. So the idea is you have your neural network here with an input node and an output node and a hidden layer. And as you're training the weights, as you're updating the weights based on a data point, for each data point, you'll every once in a while remove one of the hidden nodes. So let me demonstrate that here. So for the first data point, you use the whole network, right? Second data point, this one disappears. Third data point, this one disappears. Fourth data point, you have the whole network again, and so forth. And so the general idea behind this is that if you remove some nodes every once in a while, the performance of the method doesn't become overly reliable on let's say, one node that could have a very large set of weights. So the next thing we want to do is to implement this. So how do you get nodes to disappear, hidden nodes, every once in a while? And there's actually a very easy way to do it for a simple system like this. So here we have our simple neural network again. And so we have the output here is the multiplication of the y hidden, which is the output from the hidden layer. And so early on, if you, let's say, want to remove this node here in the middle from the input to y predicted, right, you would just set the y hidden, this value to 0. Okay, and thereby you're removing this. Okay, so it no longer contributes to y predicted. The next thing you have to do is also stop it from contributing to the update of the weights. Right, so for these weights here, they're updated through this gradient, and this gradient actually depends on y hidden again. Right, so you don't want to update this weight here, right, but this weight, of course, depends on y hidden 1, and so if you set that to 0, the gradient will be 0, right, and the weights will not be updated. So the same thing for updating these weights here, right? So if you remove this weight, right, you want to remove its influence on the updating of these weights. The gradient in this, for this layer here, is the hidden error times the derivative of the activation function times the input, right? But since we're using a sigmoid function, the derivative of this is actually computed using y hidden again. So if that's set to 0, we also avoid, well, we'll get a 0 gradient for this and therefore no change in the hidden weights. Okay, so let's go implement this. Okay, so let's talk about how we zero things out. So let's look at the YH matrix, which we want to work with. So let me print out the shape and the matrix itself. Okay, so you can see we have 11 rows and 8 columns. So the 8 columns here, 1, 2, 3, 4, 5, 6, 7, 8, that's the 8 data points. So we have 8 data points, right? And 11, this is the 10 hidden nodes plus the bias, and you can see the bias here, right? So let's just work with one of these nodes, or one of these rows. So let's pick row 1, right? And so that's 8 long. And so let's see how we can randomly zero something out. Actually, let's just see first how we can zero something out. So let me define another matrix, which I'm going to call dropout. It's going to be not a matrix, but an array. So, and it's going to have, let's start with just 8 true values. So how many is that? That's 5, 6, 7, 8. I'm going to call that dropout. So let's run this. And now you can regard these trues. Another way to think of true is just as a 1. So if I multiply these two together, right, I get exactly the same thing back I had before. Okay, but let's say I want to zero out the next to last one, right? Let me copy this down here so I can run the thing simultaneously. So let's say I want to zero the last one out, right? I can simply change this to false, right? And if I want to zero out 2 here at a time, right, I can zero these out. Okay, so the next thing we need to figure out is how to fill these randomly with trues and falses. Okay, so one way of doing this is to pick some random numbers, right? So if instead of my dropout up here, I have, I use NumPy to pick random numbers. And I want 8 random numbers. And I simply ask, so these will give me random numbers between 0 and 1, right? And so if I ask how many of these are less than a half, right, I'm going to get roughly half of them set to false. Now I have a relatively small number here, right? So you can see here it's only true 2, right? But if I do it again, right, it changes. So I can now take this here and replace this. And now I'll get, every time I do it, right, different values that are set out. Okay, so now I want to do this on the entire YH matrix. So rather than having here just a list of 8 numbers, I'm going to ask it for a matrix. And the matrix should be obviously the same size as YH. So this is the number of rows. This is the number of columns. And then I'm going to define something I call drop, which I can then define later here. So let's set this to 1/2. Right? And so now I want to work on the entire matrix. And let's see what happens. Oh, sorry, that should be a square bracket. Right? And so now you can see there are some zeros in here. And if I run it again, I get zeros in other places. Now here I wasn't very careful because now I'm also zeroing out the biases, but I can fix that when I actually implement it in the code. Okay, So let's take these two lines and go up here. So here, okay, so I move that down here. And I want to do this. I want to work on the Y hidden matrix before I add the biases so I don't zero those out. So that's one thing. So in principle here, all I have to do now is multiply YH by dropout. Now, two things. So one, before I test this, I want to set the, I want to define the dropout rate as the probability of dropping out, right? So here I have, here it's 50%, but I want to set it to something relatively small, like 0.001. Okay, so that means that here, most of the time, I don't want to drop out a node. So that means that this number here has to be 1 minus drop, right? So if drop is very, very small, right, then most of the time, this statement here will come back true and you won't drop out. Okay, so the next, the other little thing is that since you're changing the number of YH values that go into your vector, right, you're also changing the size of the output of Y predicted, right? Because if you have fewer things in the sum will be smaller. So it's a good idea to rescale this. So just divide this by 1 minus drop, right? So if I used a very large drop of, say, 0.5, right, then I would be dividing by 0.5, right, basically multiplying it by 2 and sort of making up for these lost YH values. Okay, so let's see how that works. So we run it here. That seems to be going okay. And then let's look here at how. So you can see that the validation loss and the training loss are now much more similar. There is still a dip here around 6,000. But if we go up here and look at the overfitting, right, we see that the overfitting is much less severe even though we run for 15,000 epochs. So the dropout does help in the overfitting, but of course it's still a good idea to use it together with things like early stopping and even weight decay.